Welcome, guys. Great to see you. I hope everybody had a wonderful holiday and enjoyed family, friends, cookout, whatever you happen to enjoy. Today, we are going to complete our seafloor lesson. Then next week, there'll be a module quiz on the ocean floor. That quiz will be due next Wednesday. Much like the first quiz, there's a review packet that I actually put up a little earlier, thanks to David, who inspired me. Thanks, David.
I finally found it.
Yeah, well, thank you. I was inspired. I did it a couple of days earlier. We will review on Monday to kind of reinforce it. Obviously, today we still have new material, but we will go through on Monday and do a quick review. So it might be helpful. I know it would be helpful if you guys took the time this weekend to look it over and see what you kind of questions you may have, because it's about getting you what you need. So you might look it over and see a question that you want explained, where if you never look at it and then we just pop it up on Monday as a review, I might not be able to attend to everybody's needs. So give it a look this weekend if you have a chance. It's in the folder, the same folder that the quiz is in. So the review is posted. Remember, tonight there is the mock educational handout to turn in. It needs to cover both the active and passive margins, have illustrations. Hand drawn's always a plus. I like to see creativity. You get that tactile learning when you draw and label your own diagrams rather than copy and paste. So I always love to see people going the extra mile, even if your drawings are not as the quality you would copy offline. Some are, I've had brilliant artists in the past as well, but it helps in the learning if you're the one actually putting it together. And if you do so, you can do your educational handout, and then you can take a picture of it and put it in the as a JPEG. We also have a discussion forum, just a reminder. I see a lot of posts already, so I'm very happy that you guys went and did that. So today, we're going to wrap up our seafloor. That image, it's kind of cool, actually. If you look at it, this is a coccolithophora. There's a one of those closed caption units below. When I remember to turn it on, so it gets on the video, and it kind of butchered coccolithophora. Each of these are little individual single cell algae with a calcium carbonate piece, a test or shell, and the algae is in there. They're single cells. Because they're so small, they stick together via electric charges because, positive, negative ions, and they form these little balls. They are marine algae. They're plankton. They bloom so prodigiously that you can see them discolor the water from the space shuttle flying over a bloom of these algae. Yet they're so small, you need an electron microscope to see them. And they're not famous because probably, unless you're a micropaleontology junkie, you probably never heard of the coccolithophores before, but they bloom in such, so many of them that, yes, you can see them from space. They're so small that a lot of times they get airborne and they become condensation nuclei. any cloud, fog needs to have a nucleus in its water droplets. The water actually, much like being small with charges, condensation can only occur on a surface with charges. It doesn't happen in thin air. So every rain droplet has dust and pollen and a solid nucleus in the raindrops as they coalesce, because water adheres to that solid because it's polar. You'll love the polarity of water, because next unit we're going to do the chemistry of the ocean, and we're going to be talking a lot about water chemistry. But so these guys, they have the charge, and the water droplets condense on them, so they are responsible for a lot of marine fog. So they actually alter the atmosphere when they bloom. So they're kind of a neat creature. When I was a graduate student, they're the first things that I got a chance to look at when I was taught how to use an electron microscope. So that was pretty cool. I didn't use it often because I wasn't really a micropaleontologist, but one of my lead professors was. So I got the opportunity to see one and actually look through things. And this is what we looked at, his little coccoliths. So, you know, this is coccoliths, Coccolithophorus. It's called the cocoa ball, COCCO. They make up part of the ocean sediments when they bloom. So sediments are loose particles. They can be organic, like the coccoliths have an organic origin. When they're loose and they're organic, they're also called an ooze. So that would be a calcareous ooze, being I mentioned that their shells or tests are made of calcium carbonate. There's two major types of organic sediment: the calcareous or calcium-based life, and the silica siliceous-based life. Calcium carbonate dissolves at depth. So deep ocean sediments tend to be siliceous. So you have calcareous and siliceous oozes. They make up these organic. And then the inorganic matter usually comes from deposition. So it erodes from the land and it's deposited in the ocean. So that would be the bulk of the inorganic sediments. There's also precipitates and things like that. So sediment size, looking at this is the Wentworth scale of sediments. You can see sand, silt, and clay are basically what make up our soil. Then you get little rocks, pebbles, granules, cobbles, as big as a boulder. Boulders are usually left by glacial action. The big ice is like a big bulldozer and it's pushing everything, and then it melts back, leaving glaciers. That's erratics. Cobbles and pebbles. Here, the sand, silt, and clay that makes up most of the soil. Sand is a little bit larger, a little bit heavier. So, you know, in your beach environment, you have a lot of sand. The silt and the clay usually are washed away by the waves. The sand gets eroded, it moves, but it's a little heavier and bigger. So that's why our beaches are more sandy. If you go into a bay, you can see silt built up, muddy. The mangroves grow there. Even a place like Gulfport or in Tampa Bay, the beaches have a lot finer, muddier particle. And then the clay, these are so small, they can take up to 50 years to settle out. So clay would be the most common organic out in the deeper ocean because it takes that long to settle. But sand, silt, and clay are the most common, where, you know, in California, where there's a lot of current, you have pebbly beaches. And in the Arctic area, you may even have cobble beaches when there's a lot of current. But generally speaking, our beaches are mostly sand because the waves wash away the silt and the clay, but our bays can have a lot of silt or clay in them because there's less wave action. So terra is earth. So pterogenious sediments come from the earth. They're generally inorganic. And they're the most abundant because they're so thick on the continental shelves. Also, those continental rises are made of pterogenious. But then when you get out past those continental rises, there's not as many. There's a thin dusting of more of the oozes when you get to the open ocean. But because they're so thick and built up, there's, as far as mass goes, there's more pterogeneous sediments. As far as area goes, there's more biogeneous sediments, the next type, which are our oozes, the occasional phosphate organism, but mainly calcium and silica based. Our hydrogeneous, they are precipitates. And then we always have a little bit of cosmogeneous because, you know, we sweep out our orbit. That's what a meteor shower is. And that dust usually falls eventually into the ocean. All right, so we'll look at sediments first. Here's our pterogeneous. Our first image. Coastal erosion provides the bulk of our pterogeneous sediments. You can see them here and still. So you get more of your sands, and then the particles would get smaller and smaller yet and smaller yet as you move away from your area of deposition.
Professor,
Yes.
the textbook doesn't list pterogeneous. Why is that?
I can't hear you. What about pterogeneous?
The textbook on page 106 does not list pterogeneous.
Well, pterogeneous is just a term that I was taught when I was in college. It just means from the earth. You could call it geologic in origin or terrestrial sediments, or there's many different terms to call it. I just used the term pterogeneous because that's what I was taught.
Thank you.
Mm-hmm. These are biogeneous. There's little shells. Here's little shells here. If I can make it a little smaller, they're not as grainy. These, you can see they're little, almost like snail shells. They actually belong to a group of organisms called the Forminifera. Forminifera are shelled amoebas. They have a calcium carbonate shell, so they would have calcareous ooze. This here is another shelled amoeba, but has a silica skeleton, and these are Silica Diatoms. These two are silica skeletons, the radiolarian and the diatoms, and then you have your calcium carbonate. So our oozes can be calcium and silica with a couple of phosphate, but we're really not going to talk about them too much. So pterogeneous sediments, they come from erosion, land-based sediments, usually silicone. Silica, you know, that's the most common sand. This is kind of a cool shot. I included it. It's one of my favorites. If you have a look, here's your iceberg. Underneath, far more. There's an old saying, that's the tip of the iceberg. That means you only started. There's a lot left. I say that now, and people look at me like I'm an alien because people don't talk like that anymore. But, you know, I've heard that many times. That's just the tip of the iceberg. So you can see how much of the iceberg is actually underwater. And as it melts, all of the sediments that is scraped away are deposited. So ice is a large factor when it comes to erosion and deposition, because ice and icebergs break off every spring and ride that Labrador current until they melt. So you do get deposition all the time, sediments deposited. Mainly rivers, though, and streams do most of the deposition. But the icebergs and our annual melt has a big impact. Anyway, we do have a sediment cycle. You know, they're eroded and they are deposited out in the sea, whether they're sand, silt, or even clay. And eventually they get pushed under by subduction. So the whole ocean floor is recycled every 200 million years. That's the oldest sediments right now, about 200 million years. So the sediments are generally uplifted, eroded, pushed back under. So sediments are recycled. In earth science, isostasy is the term where every change is balanced off by an equal change. And so the earth remains the same, although it's always changing. And so this is just an example of that. You're getting new sediments all the time, but the old ones are remelting. So really it's the same material over hundreds of millions of years. Here's some Forminifera. That's how you spell it, not how the AI here is spelling it. The Forminifera, these guys are super important. Again, I took micropaleontology as one of my graduate school classes, and we had to sort through Forminifera. Forminifera is really beautiful white sand. I mean, you couldn't tell it from sand with the naked eye. You put it under these microscopes, and you can see it's really shells. They're little chambered shells, and we do have a nice geologic history of them, and we know what climate they live in. So when we get these the oil drills, and they save these cores, and they send them to the Lamont Geological Observatory in North New Jersey. And then the colleges, and I went to a college in Connecticut for some of my graduate work, we would drive to Lamont and pick up samples from the deep sea core and analyze them for their fossil content, and then report what the climate was. And another college would pick up samples and they'd do the radiometric dating. And then we would paint a picture of the ocean, its currents, its climatology, and all that stuff. And these guys were huge, huge factors in that. These, they're very abundant biogeneous sediments. It's how petroleum's made, is through biogeneous sediments being deposited and then covered. And then over the millions of years, the organics separate out as oil. So this Forminifera is calcareous, it's a calcium ooze, siliceous, and like I said, very few phosphate, but a little bit. Here, this image, and you can see down here, is some plume. This is a coccolithophore, and that's how you spell it right there. There's the coccolithophore all blooming in the English Channel. Because there's so many of them, it causes the light to backscatter, and you can pick it up from satellites. So how many trillions of creatures does it take to backscatter that much light? When they bloom, they bloom. Hydrogeneous sediments precipitate out. The colder water might not hold something as well as warmer surface water, and it turns to solid. Or undersea mixing may mix and reach something saturation point. We do know, and here this is an example, these are all little manganese nodules. Manganese is a metal that if it's costly to pull them up, and manganese doesn't really fetch much on the open market. So right now it's a reserve, but if manganese ever becomes an important resource, there's plenty of it. Another hydrogeneous sediment is in the cold water. It's this stuff. These are methane hydrates. Basically, it's hydrocarbons that under cold and pressure turn into like a gel, almost like a sherbet or an ice cream consistency. These are hydrocarbons, the same stuff that you use in your grill. Propane, methane, things like that. This happens to be methane, but other hydrocarbons can build up. And because they're under the pressure of the ocean and the ice above and the cool temperatures, they're in a semi-solid or amorphous solid form. And you can actually mine them. A cosmogenous sediment, tektites, things like that, always are very shiny because they're polished by the atmosphere and they superheat as they enter the atmosphere. And they also can build up. So an overview of our sediments right here: eroded by land, that's Pterogenius. Volcanic eruptions, again, land. Now there is a huge, the trade winds blow across Africa. We're gonna study the wind patterns when we talk about climatology and oceanography. It's because oceans moderate climate, so we're gonna have a lesson on that. And the global wind patterns across the Sahara are called the trade winds. And it was named because the early imperialistic Europe used these winds as trade routes. So they're called the trade winds. And this blowing across, and it's blowing African dust from the Sahara out to sea. We actually get some here in Florida. I remember a few years back we were getting because we got some dust from that. So it actually spreads it quite a far and wide, the blown dust. Biogenious, we mentioned the term ooze, unconsolidated organic sediment, mainly calcareous or siliceous. They dominate on the deep ocean floor. Calcium carbonate dissolves, so when you get below 5 kilometers, it's all silica. And that covers 55% of the area, but mass-wise, Pterogenius still takes the cake. Hydrogenous and cosmogenous are small, but things like manganese nodules or those hydrates or other deposits can become or be commercially beneficial. And cosmogenous tektites and glasses from space are very, very rare. All right, so the thickness of our sediments, you can see on the shelves, the sediments can be 1.5 miles thick. And then those continental rises and slopes, you can get really thick sediments. And that's why the Pterogenious sediments, mass-wise, are the most. Where the ocean floor, you have a greater expanse, but it's very thin dusting of sediment. The term neritic refers to over the shelf. The term pelagic means over the deep. So you hear pelagic fish, they migrate over deeper water. Neritic is over the shelf in the shallow water. So neritic sediments are a lot thicker, but they don't cover the area that pelagic sediments do. So this image again shows you the distribution of sediments. Your pelagic clays can be in the deep water, remember, because clay is so small, you don't get a lot of sand, but you can get some clays out here. And then here's your oozes. Your oozes cover a great portion. Notice our oozes can be calcareous or siliceous. Here over the deep, you got siliceous. Actually, it's kind of interesting. Calcium dissolves better in cold water. So around the Antarctic and some of the Arctic areas, not all, but some, you get less calcium carbonate because it's dissolved better. So most of your oozes are siliceous over the deep or in the really cold. Most of your oozes are calcium based through the rest of the ocean. All right, so on the shelf, it's mainly Pterogenious. Weathering and erosion take care of that. Over the deep, you get a mix of clay and ooze. Now, when we study currents, which we will, there's a deep ocean conveyor belt, a slow movement because of density so notice there's ripples here. That's all caused by slow, deep ocean current movement. Very fine sediments and oozes. Another picture of the ocean floor. Notice there's an animal here, a fish. These are brittle stars. They belong to a group of organisms called echinoderms. There's a fish, and you can see little trails in the sediment. Very fine sediment, though. Very fine sediment. Clay would be the inorganic portion, and then, of course, the calcium carbonate or siliceous oozes would be the organic portion. And we did cover turbidites last time. Turbidite is that underwater avalanche that causes the tsunamis when it happens, or it's how the continental rise built up. You have these avalanches where all the sediments topple over the shelf and then down to the deep ocean floor, and they form what we call turbidites or sedimentary rock beds. So again, here's actually an image of turbidite. Remember those submarine canyons are from riverbeds, and you're having the river flow, pumping sediments in, and that you still get some flow in the ocean. And then you have your turbidite, your underwater avalanche, and then you have these layered deposits made from the turbidites on the continental rises. So that's how your continental rise is forming. And that is all the biogenius, or from the land, pterogenius, from the land. Oozes have to have consolidated sediment, be at least 30% sediment from shells. So they're the remains of organisms. Here, this is called the calcium carbonate compensation depth, or the CCD. Calcium carbonate is dominant until you get to the pressure of about 4,500 meters, and then it dissolves, so you get silica dominating. Also, in cold water, silica dominates right on the Arctic, Antarctic, because calcium carbonate dissolves well in the really cold temperature. A little sidetrack, one of the crises that our ocean is facing is acidification. Now, calcium carbonate is used in these shells, but there's also the buffer. It's a buffer. You take calcium carbonate in tons. So when you add acid, the calcium carbonate buffers that acid, and it cannot be used in shells. So carbonic acid, which we're adding to the oceans with our lifestyle in great amounts. You burn your fossil fuels, you produce carbonic acid.
He misspoke and said erotic earlier.
And acid precipitation. So that builds up in the oceans, and now we're disrupting this calcium carbonate cycle because the oceans, the buffer keeps that pH stable. Now we're starting to see a pH change in the ocean, starting to lower a little bit. That means become a little more acidic. And so the available calcium carbonate for marine life is starting to get less, which will impact ocean food chains and ocean life in general down the road. So we call that the calcium carbonate depth. Calcium carbonate dissolves well in deep water because of the pressure, or really cold water because of the temperature. Here's the White Cliffs of Dover, those famous white cliffs, which are all Forminifera. So here's thick deposit of Forminifera. It's called tests. TESTS for Forminifera. Shell is what they really, they are. But there's all Forminifera. White Cliffs of Dover. So here's a image of a living Forminifera under a microscope. It's kind of pretty. Here's the test. And then there's that coccolith that we led off with. Here's oozes. They don't, they're just a mixture of Forminifera with a little bit of radiolarian mixed in and other, some coccoliths. Another calcareous organism is actually pteropods, which means winged foot. They are planktonic snails that open up their little bodies like a wing and ride currents. And they have very thin calcium carbonate shells, and they're riding the currents around the oceans. That's what a pteropod is. Now our siliceous oozes, made of silica, they're more abundant in deep water or in cold water. We have diatoms, which really are probably the most abundant photosynthetic algae on our planet. And radiolarians, which are a bit more rare, they make up siliceous ooze. Here's diatoms, and then these are diatomaceous cliffs in Nevada, big cliffs of these organisms. You can go to any pool store and get diatomaceous earth, which is used in pool filters. It's used as an insecticide for natural gardening and organic farming. You spread it on the soil, and insects is kind of interesting. They have what we call sphericals. They don't breathe through their mouth and their nose. They breathe through holes in the sides of their bodies called sphericals. And they inhale and they get this little natural dust in them, and it's natural glass. It's silica like glass, and it cuts them up as they breathe, and they bleed to death internally. So we use that in ant control and other, like chicken. If you got chickens, you would spread this diatomaceous earth on the bottom of their coops because it won't hurt them, but they'll get ants or other pests, and it helps control that because of the sphericals. It cuts them up. So diatomaceous earth, diatoms are really abundant. Radiolarians, on the other hand, they are cool looking. They look like little alien helmets or spaceships. They're made of silica. They're much like the amoebas. They're single cell animal-like cells, much like the Forminifera. Hydrogenous sediments, they are manganese nodules is the most common. Evaporites, left behind here's our salts. It's actually cheaper to mine salt than it is to get it from the ocean because it takes a lot of energy to evaporate water. You heat it. So sea salt's a little pricier than your Morton salt where they just mine it and stick it in a tub. Look at this. That's your sand. White sand beaches. Interesting fun fact, the white beaches of Mexico and the Caribbean islands come from parrotfish poo. The parrotfish eat the reefs, and then it's not really excretion because it's not a metabolic waste, but when they defecate, sand comes out because they're crunching on the reef. And they produce tons of sand, every fish per year. And then the currents wash it up and it makes the beach nice white sand. So in coral reef areas, the fish basically make the sand. Whereas volcanoes, in volcanic areas like Hawaii, the lava hits the water, gets broken up, and so the sand is black. Or this is Forminifera sand, oolite sand, Forminifera, because of the plankton bloom. So, sand is not just quartz that you get eroding, like our sand is limestone mixed with the quartz from the Mississippi River, the great glacial event, and then all the quartz got washed down. We got that. We got a lot of shells in our sand as well. So we do have a large organic component in our beautiful sand. So locally, sand is different. You can see this image, kind of cool. You can see here's quartz. So this is the Pterogenious sediment mixed with the biogeneous sediment of ooze. So sand differs from place to place. So how do we study sediments? Well, a lot of those pictures you got came from deep cameras, but mainly this is the most important are the cores that we get, the core libraries and the piston cores. That's the ones I've worked with. So here, stratigraphy is the study of sediments, sedimentary rocks, can be underwater, above water, and they've been made mostly by deposition, and then if they're on land, uplift. We mentioned that the oceans, the oldest are about 200 million years old. And when you look at this is how it happens. Here you're having spreading, spreading, or actually spreading's happening here. And then it's being pushed across the ocean and subducting at the trenches. So the sediments have traveled across the entire ocean and are subducted in the trench. So 200 million years, the Pacific floor is being recycled. Of course, if you had subduction zone here, it would be less than 200 million years. But here's the oldest sediments that we know of right here at these, right by these trenches. So we do not have a complete history of the ocean sediments, the ocean fossils, and the ocean floors because it's constantly being recycled. So why do we study sediments? Well, historical data, climatology, things like that. But really, what people are most interested is money. Placer deposits are rare metals and other things that have eroded from earth, from land, and have built up. I mentioned oil and fossil fuels are found in these sediments, and then those hydrates have economic value as well. So yeah, I like the history part, and I took the micropaleontology, and it was kind of cool. But there's money and careers in geology in the resources, the natural resources. So,
Professor,
yes?
am I the only one that's on slide 21 for the last few remarks?
I have no idea.
And also on slide 21.
Rows. Does anyone else on slide 37 like I have up here?
Oh, no.
No, I'm on 21.
Okay, let me, all right, let me turn off. I will stop the share and, okay, stop share. You are sharing. Something, let me see, stop share. It appears like we have had some technical difficulties. Okay. What are you?
When you figure it out and when you start next week, could you start from slide 21 because we didn't understand some of the remarks after slide 21.
Well, I'm going to try to remedy it and go back because it's not next week yet. I'm going to try to salvage what's left of our time. I might not be able to because when I was doing this, unfortunately, this thing updated on me when I was logging in to the meeting. So I'm going to try to salvage this meeting before we call it a day and pick back up. But of course, I'll do it next week. I'll start from that if I have to. But I'm going to try to save this first. let's see what I can do. Okay, here's Zoom. All right, I'm going to close out and then reopen the meeting if I can. So we will, if I get you back, then that'll be great. If not, I'll email the class. And I have a video, or I'll run through the PowerPoint and see what we can do, but I will send instructions shortly, okay? It seems to have some technical difficulties on our end.
All right, thanks.
I still see everybody. I don't know if that's a good sign or a bad sign.